Let's go back to our definition of the center of mass, and I'm just going to use the discrete set of masses. It'll be a little bit easier to understand what's going on there. Here we've got the total mass times the position of the center of mass. This is the sum of mi times the position of the ith mass. Now what we're going to do is we're going to differentiate both sides. We'll take d by dt. We're going to assume that the masses are constant. So we're going to assume that the masses are not exchanging mass with each other, so to speak. One mass is not increasing, one is not decreasing. We're going to assume that all of the individual masses remain constant so that the total mass also remains constant. So when we differentiate with respect to time, this is a constant, comes out front, we'll just say by dt here, dr by dt. Likewise, bringing it within the sum, the masses are constant, d by dt, just on the position, dt. So what does that give us? Well, this gives us the total mass times dr dt of the center of mass, the rate of change of the position of the center of mass. Well, what's that going to be? That's going to be the velocity of the center of mass. So this is vcm. And this equals the sum of mi. dri dt, that's going to give us the ith velocity, the velocity of the ith mass. So this is just v sub I, the velocity of whatever the ith mass is. How is it moving? And then let's differentiate again. By dt, and what do we get? We get m times the acceleration of the center of mass is equal to the sum of mi times the acceleration of the ith mass. Now, let's think about this for a second. Mi times a, this is the acceleration of the ith mass times its mass. Well, that is the total force that's acting on the object. That is going to be the sum of all of the forces. Well, first, MIAI, that is the sum of all of the forces, the total force acting on the ith mass, and then we add those all up. The total force acting on each particle. Now I want to break this down into two parts. I'm going to let F sub I equal two parts. First of all, there are forces coming from outside the system. We'll call those external forces. That's all of the sum of all of the external forces acting on I. But then there will be forces on I from other objects within the system. The internal forces. Whoops, not equal, we'll say plus. F internal forces acting on I. Okay? So each total force acting on a particle, we're going to separate into two parts. One, all of the forces that are acting on the particle from outside the system, and then all of the forces that are acting on the particle from within the system. In other words, from the other objects in the system. And then, what do we have to do? We have to add them all up. But let's think about, what are these internal forces? For example, if we've got two objects, say the I object and the J object, there might be some force on object I due to object J. So we'll just call this Fij. In other words, the force on object I from object J. Well, if object J exerts a force on object I, then object I must exert a force on object J. There must be some Fji. But what direction is it in? Well, from Newton's third law, we know it has to be opposite Fij. So we know there must be a force on J, Fji, that is then opposite Fij. But then what do we have to do? We have to sum up all of these forces. So this MACM must equal the sum of all the external forces and the sum of all the internal forces. So this is going to be the sum of all of the external forces acting on I plus the sum of all of the internal forces acting on I, and then summed over all of the particles. So this sum is going to take this force and then add this force, but what happens when we add these two forces? They cancel out. For every internal force acting on I from one of the other masses, I is going to exert an opposite force on one of the other masses that is opposite this force, so that when you add them all together, they are all going to cancel out. This entire sum cancels out. And what are we left with? We are left with only the external forces. This is a very, very interesting result. Let me erase this and let me rewrite this, and let's just go back over that so that to make sure that we understand it. We found that the total mass times the acceleration of the center of mass was equal to the sum of all of the external forces summing over all of the particles. Well, what is that? If we sum over all of the particles, that is the total external force acting on the system. All of the internal forces cancel out, and all we need to do is look at the net external force. Now, let's make sure, what do we mean by external forces? Anytime we have a system of particles, whatever, there will be forces perhaps acting on these particles. Some of those forces might come from something outside the system. For example, if these are near the Earth, there'll be a gravitational force acting on the particles. They will have some weight due to the force from the Earth, or there could be some other forces or something like that. If the system is a box and someone is pushing on this box, that would be a force coming from outside the box. Those are the external forces, forces that are originating from outside the system. Internal forces would then be forces, this particle might attract that particle, and it might repel this one and maybe attract that one. But then this particle would attract that one and perhaps repel that one and whatever, repel that one, and then this one would attract that one, and or that would have to repel that one, or whatever. And then what we notice is that all of these all come in pairs, and the internal forces then cancel each other out when you add them all up for all of the internal particles. So what we're saying then is that the motion of the center of mass, the acceleration of the center of mass, is only dependent on the external forces. All of these, hundreds and thousands and millions and billions of internal forces, if you've got something with, millions and billions and a lot more than that, atoms in it with all these internal forces, all of those internal forces are not going to affect the acceleration of the center of mass. It's only the external forces. That is an amazing result. There is a related quantity which we kind of went through when we differentiated to get this term. We had the mass times the velocity. That is a very, very important quantity that is going to be related to our result. I want to go back and take a look at that for just a minute. I said I wanted to look at this for just a minute, but we're going to actually be looking at it for quite a bit more than just a minute. Let's imagine we have a single object, single particle of mass m moving at some velocity v. I'm going to define this quantity of the mass times the the mass times the velocity. This is what we call the momentum. The momentum is, as we see, a vector quantity, since it depends on the vector velocity. And the mass times the velocity, the mass is a scalar, and remember, whenever you multiply a vector by a scalar, you get another vector that points in the same direction as the original vector. Opposite if the scalar is negative, but masses cannot be negative, as far as we know. So we're going to end up with another vector that's pointing in the same direction as the velocity. The symbol that we use for momentum is a p. So the momentum vector is equal to the mass times the velocity. Now, why is this important? Well, let's differentiate this. So we've got mv equals p, and I'm going to differentiate both sides. So what do we get? Again, we're going to assume that the mass is not changing. We'll assume the mass is constant. So differentiating with respect to time comes in and differentiates the v. And then here, d by dt. So what do we get? We get dp dt equals m dv dt. But what's dv dt? Well, that's the acceleration. This is ma. And what is m times a? That is the total force acting on the object. So this equals F net acting on the object. So what we find is a very interesting result, that the net force is the rate of change, the time rate of change of the object's momentum. And if there is no net force acting on the object, the momentum does not change. In other words, the momentum is constant. That is a very, very interesting result. Now, how does this apply to a more extended system? So let's imagine we have a system of particles, and let's define the individual momentum for each particle. So P sub I will be mi vi. So that's the momentum of each of those individual masses. And then let's define the total momentum. What's the total momentum? Well, we'll say that the total momentum for our system is the sum of all the individual momenta. Actually, there's an interesting point. Let me put that in there. When we're talking about the momentum of one object, the singular is momentum. But if we're talking about momentums, don't say that, for a number of particles, the correct term is momenta. So not momentums, but momenta. We have talked about the momenta of a number of particles. So what's the sum of all of the individual momenta? We add these all together, and we get the sum of MIVI. But wait a second, we already saw that before. That is the total mass times the velocity of the center of mass. We had that step in an earlier derivation. Well, that's a very interesting result, and let's just write that down. So that the total momentum of the system is equal to the total mass times the velocity of the center of mass. So when looking at an entire system, the total momentum of the entire system we can get by taking the total mass and multiplying by the velocity of the center of mass. So if the center of mass is not moving, even if these are moving around it, if the center of mass is stationary, then the total momentum is zero. That's a very interesting result. Now, what if we differentiate this result with respect to t? We get dp dt is equal to, again, assuming mass is constant, m dvcm dt, which is, like we saw, acm, m acm, and we just saw that that was the total of all of the external forces. So this is the sum of all of the external forces equal to dp dt. If there are no external forces, what is this telling us? If F external equals 0. So if there are no external forces, there could be as many internal forces as we want, but if there are no external forces, then if this is 0, dp dt is 0, which means P is constant. In other words, the momentum of the center of mass is constant. That is a very amazing result. This is the conservation of momentum. So, like we saw the conservation of energy earlier, this is the conservation of momentum. If we've got a system of objects and there are no external forces, or I should say, the net external force is 0. There could be external forces, but if they all cancel out so that there are no net external forces, if the net total external force is 0, then the momentum of the center of mass is going to be constant. We've got conservation of momentum. That is a very, very interesting result. But what does that mean? If P is constant and m is constant, that means the velocity of the center of mass is constant. The system moves with a center of mass, the center of mass of the system moves at a constant velocity. That's a very, very interesting result. Sometimes, for some complicated systems, it's easier to look at the system, what the system is doing, in a special frame of reference. In other words, to imagine that you are stationary with respect to the center of mass of the system and look at it from the perspective of the center of mass. Sometimes that can make looking at what a system is doing very, very easier. You can separate out the motion of the whole system in terms of the motion of the center of mass, and then you can look at the motion relative to the center of mass. What is the system doing relative around the center of mass? Let's take a look at that.